Yo, what's up? It's day 4 of the language development stream. Let me make sure the stream is working. It'll probably take a few minutes to catch up. Just want to make sure I can hear myself and then we'll start. Starting up the treadmill. Gotta have the treadmill. Alright, I can hear myself. Let me make sure there's no audio coming through. Okay. Okay. So, we got a few bugs that we need to fix. It's a disaster. I wrote a bunch of bugs into this stuff, and I only discovered them yesterday as I was going further and reviewing some stuff. So right here, we check if the character is greater than or equal to A and then less than Z, which means that Z won't be a recognized alpha character. So we need to add that equal sign there. I have a few other to-dos. Let me actually get rid of that. Wow, I already lost it. Imagine that. To-do, fix this, done. Okay, so these offsets need to be fixed too. So we read the I and int, and then we just progress the character counter by 2 instead of the full size of the character. Instead of the full size, the keyword, that's fixed. Alpha. So this, every time we come across a sequence of alphanumeric characters that aren't a recognized keyword, we store it as a variable. And so, like, if we have X multiple times, or any keyword multiple times, we'll just keep storing it into this array. I mean, it's really large, so it's not really a problem, but eventually we want to hash it. So this is just a long-term thing that I don't want to worry about right now. So, just something to mention. I never really explained this modulo system very well, and it has to work. I also didn't explain that when you do a bitwise AND with something to modulo, you need that number to be a power of 2. So hash table size, I think, is like 2048. Yeah, so this is a power of 2. This is like 2 to the, man, I don't know, like 2 to the 8 is like 255. Times 2 equals like 512 times 2 is like 2 to the 11 or 2 to the 12. But it's still a power of 2. That's what I'm saying. So we can break it down to a very simple case where, let's say, 8 is 2 to the power of 3, right? And in binary, that is 1, 0, 0, 0. And you subtract 1 from that, and then you get 0, 1, 1, 1. And so when you bitwise AND that with any other number, you're ANDing together all those 1s and cutting off anything beyond that 8-bit right there. And so you AND it, and then you get 5. So that's exactly the same as moduloing that number with that power 2 number in general, right? I don't think I did a good job of explaining that, but that's good enough, and I'll just leave those notes in there for you. That's our last to-do, so we don't really care about that. So let's just pick up where we left off. So let me, oh god, I never moved it to day 4. Let me do day 4. Let's paste it in here. Yeah, okay. Day 4, let's go to that link. I don't know, we're going to kind of go off the rails from crafting interpreters now. Parsing bugs. I guess I could undo all these changes in day 3. Yeah, okay. Now we still have all those changes in day 4. We just make sure. Yeah. Okay, so why is your YouTube channel so good, bro? OMG, Kevin Morales, bro. I know who that is. What's up, bro? We're doing statements today, or the goal. Did I fix all this already? Let me make sure we can loop. So I'm just gonna get started, and if you have any questions, feel free to ask. I'll try to explain what's going on. We moved this into a new folder, so we need to set up the compilation. Okay. Cool, 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 cool. Okay, so we commented out the prat parsing. Love you, bro. Love you too, bro. So we commented out the Pratt parsing. We don't care about that anymore. I guess we should. We're not going to do any of this stuff. Let's just comment all this stuff out because we're going to start adding statements. And we need to make sure that all looks nice and good before we start parsing more things. Thanks for the emoji spam, bro. So, yeah, right here. So, this is another thing I want to get into, but I want to start adding a bit more robust error checking, which means that we have two separate paths here. When we want to loop, we read the input, we prompt for input, we read it, and then send it through the parser. Otherwise, we just send in a fixed string with a different name that isn't tied to the global input memory. So I want to copy that memory over. So we'll do void h, short for handmade, stir copy. And we'll do char destination, char source. And then we'll just, we'll make sure that these aren't null. So we'll do like if dest equals, or you can do the same thing right there. We'll return 0. Let's actually return int, because I also just want to return the length of this, just for the hell of it. If destination is null, if source is null, otherwise let's do int count equals 0. And then we can do while source that we're copying from does not equal the null terminating character. My wire keeps falling out. Okay. So while the character from the source that we're copying from isn't the null terminator, we'll dereference the destination and set it to the same thing as source, and then we'll increment the source pointer and the dest pointer and the count pointer, or the count amount. And then we will just return count when we're done. It should work. And now, how do I want to do this? We can do h, we can do int, I don't know, why not, input size. Input size equals h stir copy. We give the destination, which is input. That's some global memory. And then we'll do test string. And then we'll send in input to the parser. And because these two paths match, we can just pull this out right here. See if that compiles. Okay. And let me just make sure that it copies everything over correctly. And input should have 1 + 1. Yeah, there you see it. So that stir copy thing works reasonably well. We have 5, which is 1, 2, 3, 4, 5. Yeah, okay. So I will go out on a branch here and say that that handmade stir copy function works. So now we're sending in that input, and we're doing everything, and we read all those tokens. We have a number token, a plus token, a number token. Cool, so that should work. We just increase the size, why not? And now we'll start doing some silly stuff. So I want to start adding statements. Statements are, yo, who in here knows? Yeah. Classic Kevin Morales chat. All right, so we're going to add statements, and they are one layer above environments, or no, sorry, expressions. It's like a whole new type. Statements can contain different expressions. Bro, I'm at McDonald's RN. Nice, bro, sick. Everyone, Kevin Morales, 5913 is at McDonald's. What do you think he's going to order? Where should I put statement? Okay, we'll just do type def struct statement. Statement, that's just how you do it. We'll do statement type, and then union, the classic union data, and then we'll have declaration, statement expression, expr. I think that covers all of our bases. For now, we got to add a type def enumerator for it. Enum, statement type. Then we'll have statement none. Decl for declaration, like you're declaring a variable and a type. And standard expression, yeah. And now we need to make types for these. Let's do another type def struct. Then we'll make one for expression. And what do we even put here? For a declaration, I have like token int stored, so like I'll do token type. This will be the type of the variable that you declare. There will be an expression for the variable, and then, or I guess the variable is just going to be an identifier, so we can do int var offset into that array that we copy everything into. And then we can just do, I can't quite remember, I guess we'll figure it out, but you need to set it to something. So like we'll do, just to give you an idea, like this is a declaration statement. You have the type, you have the identifier, and then you have the expression that it's equal to. So yeah, this would be like a primary expression or something. And then for the expression statement, like this is, I don't know, if you just do like 1 + 1, you don't really set it to anything. Or like a print statement or something. So this will just be expression E. That's all you put in there. Let's make sure this compiles. Of course not. Why would it compile? We are not doing something right. Whoa, statement declaration, redefinition. Okay. Oh, sorry. Declaration statement. So this order, it conflicts with the enumerator that I defined, statement declaration. When I define any kind of statement type, I usually, like, this is just the way that I do it, but I put whatever the enumerator type is first, and then, I'm getting this backwards. Whatever the identifier is for that, like, overall type, like statement, underscore, and then the actual type for it. So when I declare the actual statements, I just do it the other way, which I guess is pretty confusing, but I'm used to it. Sometimes it trips me up. I don't have any better ideas. Expression statement and declarative statement, declaration statement. Okay, compiling successfully. We have the statement types. We have, oh yeah, so let me expand on this thing up here so that you have a better idea of, I don't think I have it anymore. Oh, here we go, it's down here. Yes, so right here, you can see, getting kind of hot. You can see all of the precedences, the precedence I. So equality comparison, we're going to want assignment in there. That's going to be something like the assignment. Or does it take top level? I'm not sure. I guess we'll figure it out. We can mess around with the statements later, but then we'll have this kind of symbol and then a comparison. Yeah. Yes. Expression or expression, equality, comparison. I think it comes right here. Expression can be an assignment, can be, or some other type. We'll have like calls, but let's not worry about that yet. Those are for functions. But right now we're going to worry about assignments because I can just drop in that code right now. This is the code that we're going to be working with. Right here, we're going to do int x equals 1. We need to add new lines to this. Y, z, let's just set z to 0, let's set y to 2. And then we will do z z equals x plus y. This is all we want to, like now we're going to have multi-line code, or we're going to have declarations, assigning variables, adding them together, stuff like that. Let's make sure everything still compiles. Let's just run it and see what happens. We're probably going to unhandle token type, token integer. Okay, that's good. So I also want to add more robust error handling. And this is where we're going to start getting very silly. Where do I have lines? Do I have a line count yet? When we have an error when we're parsing, this is similar to what crafting interpreters does, but he has a line number in the tokens, and so we're going to keep track of parser line. That's the line the parser starts on. In lines of code, like in VS Code, you start on line 1, so that's what we're going to do. We're going to start on line 1. And then from there, I guess we're good. And we'll just tune the parser a little bit. So we'll check for white space. If it's white space, it would be a pain to do it in the isWhitespace function, so we can just add a little check right here. It doesn't really matter. Add a check for a little new line character, and then we'll do parser line plus plus. And we're doing something wrong. Imagine that. That's because, yeah, okay. Forgot a semicolon. So we're going to increment the parser line, and now we also want to, just to make debugging a little easier, we're going to have offsets. So we're going to have input lines. Why not? Yeah. Whatever. Int input line count. 0, or do we start on? That's how we index. No, we're going to start on line 1, just to match with the parser line, because that's what the token is going to point at. And inside parser lines, these are just going to be pointers to offsets in the input. And so down here, we're going to do input lines equals input plus I, I'm pretty sure. Input lines, input line count, plus plus. Got to advance it. And I think that should work, because once we hit, let's actually increment it right here. We'll increment I, because that will start us at the beginning of the next line. It should work. We can figure out later if it doesn't. But this is just the first step that we want to take. And I think that's... No, and then when we... This is going to be quite the hassle. But we're also going to need to store that line when we make a token. So, like, we could just duplicate everything. We could make a function, like void add token, then we like send in the token, and then we just push it back to tokens, token count plus plus equals t, and then we do t dot line equals parser line. Just to compress everything. Yeah, sure, we'll do that. Why not? Why not? So we still need to create the token on the outside, and then we'll just replace all these, token t. So that will automatically handle the line placement for us as well. Tokens, token count, plus plus. Let me just find every instance of that. And yeah, let's just replace every instance equals t. Get rid of that semicolon. And then we'll just replace it with add token t. Okay. Add token recursive on all control paths function will cause runtime stack overflow. Oh, yeah, I also replaced that. We don't want to replace this one. Tokens, token count, plus plus equals 2. Okay, so this will probably lead to errors that we're going to need to resolve. but this is a good enough start. And so then when we have an error like that, like, let me just run this. We'll see what happens, and we have error unhandled token type right here. Okay. So when we have an error like that, I'll just make a new function called token error, and then we'll pass in the token, tokens, next token, and some kind of string. Error unhandled token type. Right? And then we'll just make this function. Let's do it like right here. Do void token error of token t and a const char pointer to an error string. And so sometimes, like, what if I don't want to? What if I want to pass in null or something? So I'll just do like if the string is null, we won't print it, else we'll print it. We'll do printf error token error. We'll do token string t.type, and then we'll have the message. Well, this is for if the string is valid. So in case it's null, we won't print it. And then I also want to print out the line. So print error line. And we will pass in token line. So int line, let's do print error line, t.line, because now we're storing the line index for every token that we parse. So just as an example, int x equals 1, int y equals 2. This is line 1, this is line 2. Let's say we have an error at this token y. When we store this token, we know that we're parsing line 2, so this will just give the programmer a bit more error message context. It'll just help us in debugging long term. And then we can do, well, parser line is the current line. I already forgot. Input lines, okay. Input lines at line. This will index, this will point us to the beginning of this line. We can do char string equals line, and then we can do, I guess we can sprintf everything, or how do we want to do this? It could just be sloppy, like char temp error line. Why not? Let's just have another huge input. Then int temp error line count. Start at 0. And we'll just reset it every time we call this. Temp error line count equals 0. And then we can do for. We'll dereference the string. This is an array of pointers, so we can reference it like this, and we'll still get a pointer. If string does not equal the null terminator, or doesn't equal a new line, because we only want to print out the line, all the characters in that line, we will do temp error line int I equals 0 at I equals dereference the string, and then we'll do string plus plus, and then we'll do, I guess we can do I plus plus. And then we can print it at the end. Printf error line, oh god, temp error line. I think that should work. It does not equal that or that. Syntax missing. I'm doing something very wrong. How could this be wrong? Let's just comment it out and see what happens. dereferencing the string. Do I need to wrap it in parentheses? If it doesn't equal this and it doesn't equal new line, \0. Let me just do a test equals. Dereference the string. There's always something that throws me off. So that works. So what's wrong with this? For while. I meant to do while. Oops. That was silly. Okay. So we're printing the error line now. Let's just see what happens. Error line, int y equals 2. Hey, look at that. Amazing, isn't it? So this is just to give us a little bit of context to what's going on. And we can even make it pretty. We can add colors to it, and VS Code can handle colors in the console. I think it's called console text color escape sequence. ANSI escape sequences. ANSI escape codes. Okay. Well, I don't want to parse all this, so let me just see if they give it to you straight. This might be too much of a time sink. Wait, I have them saved somewhere. Yeah, that's it. We'll look up an older project. I think it's in... Yeah, it's probably here. So we can go to constants. This is that engine that I've been working on for a very long time. Yeah. So I got them here. Guess we could just... Why don't we just copy them all over? Who cares? Okay. So let's... Oh God, where was I? Okay. Let's just drop them in at the top right here, or after this. Yeah. Okay, and we will do red. Let's get red, and then we'll need to reset it. So we can do error line, token error, go back to this function. We drop them in around the string that we're printing. So we can do red, and then reset. And now you'll see that we have it in red coloring. Isn't that so cool? But remember, you got to reset it. You got to wrap it in the commands. I think we can make it bold too. Let's do bold. Oh no, we have it right here. Bold red. We'll do B red. Again, this I don't think this will work in the Windows console, but it works in VS Code for me, so just to make it look pretty. Otherwise, it'll just print out gibberish. Yeah, there you go. Totally unnecessary, but just something cool that we can add. And we can see exactly where the error occurred. And we only print out so much of that line until we hit either the null terminator or a new line. We're parsing everything. We're not printing out the token error. Or are we? Token error. Oh, we are. Token, an unhandled token type error and expression evaluation not evaluating. Let's add a new line here. Try it again. Token int, unhandled token type. That's because we're still evaluating these as expressions. You can see, I think we're probably still calling it in our main function somewhere. Yeah, E equals expression. So we're printing out the tokens and we're evaluating the expressions. Now we need to start adding the statements. So I just wanted a big tangent there. But remember how earlier we added statements? We'll do the same for We'll do the same thing that we do for expressions. We'll have an arena of statements. Statements, and then we don't really need program. We can instead have statement block statement children. Why not? 2048. These will be pointers. Block statement children count equals 0. Where is our expression count? Right here. And we'll have statement count. So this is the arena. Arena for statement allocation. Sequential list of statements within blocks. Which means that we're just going to start appending to this immediately, because in any program of our language, you're already going to be in the global statement block. And I guess we'll have this block statement builder, 2048. These will be more pointers. And block statement builder count. I can explain this later, but you could have nested blocks. So a block is where you wrap it in curly braces. You have like int x equals 1. And then you could have another block in there for like int y equals 1. Or maybe you could even declare a local variable in there, so like int x equals 1 again. And this is valid. And these are blocks, so you open up this block, you add a statement to it, and then you open up another block. But then it could throw off how you iterate through those blocks, so we're just going to have a little builder thing to keep the memory separate. And then once we've hit the right curly brace at the end of a block, then we know all of the statements within it, so then we can append it to that block statement children thing. It'll make sense when we do it. I was using linked lists before, and that got kind of cumbersome. So again, we're not worrying about this yet. We just care about statements and block statement children. So we'll go back to main. And let's do all this, like statement count, block statement children count, block statement builder. Just set all this to 0. Okay, we're going to print the tokens, and now we're going to do for while next token, tokens, next token does not equal token end of file. Okay, tokens dot type, yeah. Okay, so this will be the main block that we use to parse, to construct statements. So we can do, yeah, I guess we'll just call statement. Yeah. We'll call statement, and we will append it to, it will return a pointer to a statement, and we will return it, append it to statement block children. Statement block children count plus plus. Okay. I'm doing it wrong. Subscript requires array or pointer type. That is because we haven't defined statement. Would you imagine that? Let's go to where we define expression. I think we're safe if we just put it up here. Statement, statement. And we will return, let's just do statement, s equals statements plus statement count plus plus, and return s. We're still getting an error. Statement block children, undeclared identifier, statement block children count. I can't see where the edits have been made. I usually rely on that. Like you see blue and green coloring in there. Oh well. Block statement children. I got it backwards. Okay. Now we're going to start parsing statements. So again, you can either have, it'll depend on the token type. If tokens, I guess we can do like, we get fancy. Tokens, next token. Increment it, right? Or maybe not. I guess we can increment the token count in the expressions. Else, okay, so if t.type equals token int, this is, if we see a type, for now, like of course you can do casts and stuff. You can like cast something by wrapping it in parentheses and C, but all we're going to care about is like if we see int, then we're just going to assume for now that it's a declaration. And so then we can do, I don't know, decal statement. Yeah, why not? Then we can do, we need to declare a null statement up here, s equals null. And then we can set s to the declaration statement. That will allocate that memory for us. Otherwise, like all we're supporting right now is declarations and standard expressions. Then we can do s equals expression statement. And of course these aren't defined, so we're going to do decal statement and expression statement. Return null. Okay, so that's all working. And so, just copy this. Statements plus statement count plus plus. Return s. Okay. So we will allocate memory for the statements in these functions. Okay, so again, we have the token, we have the integer token. We're going to, if we hit declaration statement, then we know that the first token is some kind of type. And so we can set s type equals, do like, do that same thing, token, t equals tokens, next token plus plus, we'll increment it this time, t.type, oh, I need to do, oh, they're both enumerators, so we can do statement declaration as the type, s data declaration dot type equals t dot type, and that will store the integer token there. So we read the integer token. Int x equals 1. And now we want to store, the next token needs to be a variable. Token var? Yeah, okay. Yeah. So the next token needs to be, we can do t equals tokens, next. We won't increment it in case there's an error. If t.type equals token variable, else token error, give it t, expected variable declarator after type. You don't need a new line there. Then we'll do processing error, plus plus, return s. I guess we could set this to null for now, and then once we know that there's no errors, we can set all the stuff there. Oops. Let's just call this t type. This is the token for the type, because I don't want to t-type type. Man, that is disgusting. Whatever. Just so we don't allocate memory in case there's an error, but that doesn't really matter, and I'm kind of making it needlessly complex. But again, who cares? So we're checking if we have the variable name, and in that case, you can do, let's call it the var token. Let's just call this the type T for type token. We'll call this the var token, vart. We'll call this the type token, type T. Okay. If this is the variable token, then I guess there's no problem, and then we can do s data decal var. No, this will need to be an expression. Sorry. Okay, so I'm getting a little confused. We need to add a new expression type. We still evaluate it in primary, but it can also be a variable type. And so we'll add, oh, and we also need an assignment expression, but I think we have that. Yeah, okay. So let's make two new expressions right now, actually. If I can find them. We'll need a variable and an assignment expression. And we can make them right here. This will be assignment. This will be variable. For a variable expression, remember that we're doing that really sloppy thing and just storing that offset into that global var offset array. So this is all we care about. And then an assignment, we need the variable. We need the left variable, which is the variable expression. And then we'll have the right expression, which is what we set it to. And the operator is always going to be equals. Declaration statement. Yeah, I'm not setting that right. But we're getting there. Variable expression and assignment expression. We will add these to the union. Assignment, variable. Set this up to primary. Okay. We're getting there. And I wish I had those little, whatever. Declaration variable. This will be left. And we can do, why not? Set it to null. Declaration left. Am I doing this correctly? I can't remember. No, when we hit this statement, when we evaluate this, we're going to do it differently. How we're just going to store the variable offset. That'll be an integer. And then we're setting it equal to an expression. Or do we just take the whole expression? Because in a sense, this also is an assignment. I guess it doesn't really matter. It's totally up to us. So, yeah, I guess we can just call it an assignment. And we'll have that. Yeah. Okay, so we will just do E and E equals expression. Yes, I think that should work. And then we can do E equals E. Okay. And then we also need to check if next token, or sorry, tokens, next token dot type equals semicolon. We can just start terminating all of our expressions with semicolons. And we can just do assert, whatever. Let's just debug break right here. This is just something you can do in VS Code. And this will pause the execution right before we go any further, just to make sure everything works. Or you can just set a breakpoint, like it doesn't, yeah. You could also just set a breakpoint. Debug break just sets a breakpoint right there in the code. So we get to expression when we have that token variable. And now this is where we need to add those new precedence types. So we have expression, assignment. This we'll call assignment, and then assignment we'll call equality. You're just jamming this in between the two precedence levels. Return E. And let's also add a clause for, right here. You want to check if the next token type is a token variable. And if it is, then you're going to do E, you're going to do all this stuff. Expression count, E type equals expression variable. E data variable var offset equals that token dot data dot var offset. And then you're going to do next token plus plus since we read it. Okay. So this should return a variable expression. You allocate it, you set the data inside of it. And now we're going to do assignment. So we're just going to check if eType equals variable, expression variable. Then we're going to do something like last E equals. This will be an assignment expression. Go to, remember what it looks like. You're going to have a left and a right. Yes. Yes, yes, yes. You can just call this left. We're going to have a new expression, expression E. We're just going to set it to expressions plus expression count plus plus. You're going to allocate a new expression. You call left left, or you're going to assign the type to expression variable assignment. E data assignment left equals left. And for the right, you're going to read another expression. And I think that should work. I need to piss. I'll be right back. How far have we been going? Almost an hour. Give me like 2 minutes. I'll be right back. Just taking a little break. Okay. Where were we? I'm losing steam. Keep going though. Let me make sure the stream is still working. Make sure I can hear my audio. Wouldn't want to stream for 2 hours with no audio. That would suck. That would just be embarrassing. But the stream is catching up. Give it like 1 minute. Yep. I can hear my voice. Cool. Okay, where were we? Let me start the treadmill. Okay. Okay. what were we doing? We were doing assignment expressions. That should hopefully work. And then we store that assignment expression into the declaration statement. We'll have the type and the type of expression. And then we want to check for the semicolon. Just do that right here. If it does not equal the semicolon, then we're just going to do a little error. Expected semicolon after expression. Return S. Just do it right down here once we know for sure that we're allocating it. And then we'll do next token plus plus, because that means that we definitely read a semicolon. So let's just see what happens. Wow, look at that. Let me just step through from the beginning to make it crystal clear what's happening. So we have an array of statements that we're appending to. We're just going to loop through every... We're going to make sure that this only happens when we... how do I say this? We're going to start the loop through all the tokens right here. And we're going to start constructing statements that we're going to append to more global memory. I'm going to step into it, or that's... I haven't even started debugging it. Okay. So we read int x equals 1, y equals 1, etc., etc. Now we're going to step into this. We see that the first token is an integer token. You see int var equal num, semicolon, int var equal num, semicolon, int var equal num, semicolon, var equal var plus var. Cool, semicolon, end of file. Damn, okay, those are all the tokens reading incorrectly. We'll step into the declaration statement. The type is going to be a number. We're going to have a variable, checking if it actually is variable type. Assignment, equality, comparison, terms, factors, unary, primary, and then it should be a variable token. Okay, cool. And the offset will be 0 because that's the first. X is the first thing that we store there. Int x, that's the first variable expression that we come across. So in that big array where we keep duplicating all the strings, that's where we're going to store it. Going to advance to the next token, going to come all the way back out. Equality, assignment. Okay, so it was a variable expression. Going to set this to an expression, an assignment expression. Left and the right. Assignment should be a primary of 1. It's going to be a number. Oh dear. What is the next token? Next token. It's an equal sign. We forgot about the equal sign, and now we're going to have an error. Oh god. Because we returned a null expression because we didn't recognize the equal sign. Okay. Okay. So let's go if tokens next token dot type is not equal token equal. Gonna have an error at this token. Whatever, I don't know. We can throw in some all caps, lowercase, who cares? Expected equal sign after variable. Yeah. Yes. I don't know. We'll see if this is a problem later, but I can't think that far ahead. But this could probably lead to its own problems. We'll do processing error plus plus, return E. Otherwise, move on to the next token. Expression, step into that, assignment. Next token is the equal sign. We'll advance to the next token. Go into equality, comparison, terms, factors, unary, primary. Oops, I stepped over primary, but it'll tell us if I mouse over E primary, and its data is T integer 1. Okay, perfect. Okay, we are returning something. E is an assignment expression. Okay, cool. And what is the next token? It's 4. It's a semicolon. We step past that. We create a new statement, a declaration statement with type token integer. Cool. With that expression, we return that statement, return it back up, and that goes into the first block child. Let's do it again. We should return another assignment expression. This time, its left is going to be a variable that is going to push step into var offset 2. Remember, 0 is for x. 1 after that is just the null terminator, so we can print these out easily. 2 is going to store y. That should work. Yes, yes, yes. Another one. Cool. Step into this. This will be an expression statement where we do x plus the other thing, but we haven't filled that out yet. So we need to do statements, like do expression, E equals null, E equals expression. Then if, I don't know, processing error. If we do have an error, we'll just return S. Yeah. S equals null. You can do this in any order. I don't know if this really matters. I just want to check for errors first. And then we'll do S. Type equals statement expression. S data expression E equals E. Okay. And an expression will return variable plus variable. I think this will work. It's first one, second, third, fourth. Step into this. It'll be an expression statement. And we didn't do. I guess we can just step into this and figure out what we're doing wrong. Forget something every step of the way. Expression statement, expression, assignment. This will be a variable token. Oh, okay. Okay, so we have a, no. We shouldn't, yeah. Yeah. Yes. I think this is actually working as intended, because then the right expression will be, oh, binary. Huh. Okay. Step into it again. Expression, assignment. Step into another expression, assignment, equality, comparison, terms, factors, blah, blah, blah. Oops. It's a variable. The variable is offset 8. Again, we have int x, int y, int z, z equals x plus y. Every time, it's just the stupid way that I'm storing this stuff. Every time we come across a variable token, we store it into a new fresh slot of that memory, which is why it's the same value, but they have different offsets. We're just pointing into where they begin. So, again, very silly. But, and I can't really verify what it is, but it's a variable. Let's come back up. Terms, okay, so we're adding them together. E.right, E is a binary, and its left and right are variable expressions. Okay. And E is an assignment where its left is a variable and its right is that binary, and the binary left and right are variables. Okay. So where is the problem happening? Token type does not equal end of file. What is the next token? 20. This is a semicolon. I forgot to read the semicolon right there, because you need to add a semicolon after every expression. Just do that right here. Just copy this. In the book, it it condenses all of these checks down into a single function. But I'm feeling rather lazy, and of course we can just shit up the code more and more until I'm comfortable with compressing this all. Again, I just want to get it to work. So we'll just add a little check after that. Check for a semicolon. Do yes. Expected semicolon after expression. Okay. Once again. Come back out. What is the next token? 20. It's a semicolon. Oh, that's because I added that, and of course, next token plus plus. Oops, yeah. You can see why turning this into a function saves you a lot of time, because you don't need to debug so much. Again, I feel like there's a trade-off there, because yeah, it would save us time, but then debugging the function itself and then figuring out all these edge cases, because what if I don't want to increment exactly that way, like for this general purpose function, what if I want to increment the next token separately? And so that'll just shake out over time. Next token. Cool. Next token should be the end of file. We're at 21, which is the end of file. Cool. Cool. Okay. And of course we skip all this stuff, so then the next step would be to start printing out all those statements. And we can start handling, we can do like a panic mode, because what if you're missing a semicolon? Let's just do that. Let's just say that we forgot a semicolon right at the top, and let's see what happens. Okay. So expected semicolon. Token var, semicolon, unhandled token type, yes. Okay. So we want to handle that with if processing error, enter like a panic mode thing. Skip until another semicolon. Yeah, why not? There's a bunch of ways you can do this. It's called like synchronization. You can get a more robust version working from crafting interpreters. We'll say while tokens next token plus plus dot type does not equal. I guess we can save that. Well, it doesn't equal semicolon. This is where it's going to get tricky. We also need to check if tokens next token dot type does not equal token end of file. If it does, we're going to want to break out. We can figure all this out. Let me remove that semicolon here too. Reset the processing errors so that we can keep going. And then we'll also have another one like errors plus plus, just for general errors. Int processing error, we're going to have int errors if errors, and also jam it in here. Loop or just return. Yeah, just so that we don't go any further. And we'll stop it at parsing, or we've already tokenized it. We're scanning all the tokens now to make sure that they form coherent statements. And if one of those statements is broken, then we probably shouldn't run it. And so that's just what errors is guarding against. We're going to reset processing errors so that we can go back in and look for the next statement. While we're going to do next token plus plus. And let's just see what happens. So press F9 to set a breakpoint there. So we did get an error because we were expecting a semicolon. That's interesting. Error at line, expected semicolon after expression. We should be printing out the first line because that's what is missing, the semicolon. Let's step into it and see what happens. This isn't really, I mean, you know, we could make sure that for debugging purposes, all the code we're writing is correct. But as we write more complex programs, even we're going to get confused, so we might as well add decent error handling tooling at this point, just for our own sake. Declaration statement. Next token, semicolon. The next token at token 4 is going to be an integer, so because we already go past that last token, we can just do something like, I mean, of course this is going to be sloppy, but we can do something like tokens, next token -1. We're always going to be like at least the first token. If the first token is end of file, then we're not going to execute any of this. Otherwise, we're going to be past the first token, so I don't think there's a risk of indexing out of bounds. And we can just replace like expected semicolon. We can just replace all these with -1s. We only have 2 of them. Error line. We still have that error line. That same error line. Okay, let's just keep trying. Declaration statement. Next token, -1. This is going to be token 3, which is going to be the number token at line 1. So why is it line 2? That's interesting. Line 1. Input lines. Oh, that's because this... Yes, okay. So this is an error in our parsing, or a little bug I wrote, because we never initialized the first line to the start of the input. When we increment, we're going to set it equal to line y equals 2, int y equals 2. Let's go to parser. Parser line plus plus. Yeah, just a parser line. It's stopping us from doing that. Yes. Okay, and then right before we call parser, we can call that. I don't even know if we need that anymore. What do we do? Man, I already lost it. Parser line plus plus input lines. Press F11 to go to definition. Input lines. Input line count. We probably don't need that because parser line will just know which line to go to. And then before we call parser, in our main function, we're going to set the first line equal to the beginning of the input. Page down, yeah, whatever it is, parser, right here. Going to do input lines at 1 is going to be equal to just the start of input. So this should give us the correct line. There you go, int x equals 1. You see how there's no semicolon. Token error at the number, expected semicolon after expression. Hey, that looks like a decent error to me. So now we're going to loop through until we hit the next token. If it doesn't equal end of file, oh, oops. If it does equal end of file, then we're going to break out. This is my bad. Next token, next token, next token. Okay, so we hit the semicolon, and next token is 8, which is the semicolon. So once we do hit the semicolon, we're gonna need to advance it one more time. We could just, yeah, this is silly, but we just do. You know, because it's an end of file. If it's an end of file token, we want to know that we're there, so we should just do this again. If it is a semicolon token, then we do next token again. You know, kind of sloppy. You can have better error handling. This is my code and I'll do what I want, god damn it. Okay, so we have an error. The next token is 9. There's no error parsing that. Okay, and we forgot a semicolon after that one. Let's keep going. And we hit the end of file, and then we break out of it, and then, okay, cool. Cool, 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 cool. Okay, that's pretty cool, isn't it? Error line, I guess we should also print out the error token error. Let's add error line, like, and then the actual line number. Let's allow for like 3 lines there. Red. Before we color it, let's just do the line. Okay. Error at line 1, error at line 4. Isn't that cool? Because we forgot semicolons. And now let's add those semicolons back in. Of course, there's going to be bugs in this. There's always bugs in the stuff that I write. We're going to need to pull them out in the future. Should be good enough. But what do we want now? Now, I guess we should print out. We've created abstract syntax trees for the declaration statements. So now what we should do is print them out. Remove these breakpoints. If we have any errors, we won't go any further. And now we'll do for int I equals 0, I is less than block statement children count, plus plus I. Again, whatever this means, this is just where we store the statements. Is less than, and then we're going to want a print statement. Print statement, and we will pass in s equals block statement children plus I. We'll pass in s. Block statement children. Oh yeah, so it's an array of pointers. So that would just be giving us a pointer to a pointer if we add I to it. And now, because we don't have a print statement function, that's giving us an error. So do we have print expression? Yeah. Let's go to that. Remember how that looks. Print expression right here. Okay. Now I'll add void print statement, or print statement, statement s. And we'll switch on it, s type, case, default. I love my defaults. Statement, declaration, statement, expression, and then this we'll call print. Yeah, I guess print expression. Yeah, cool. We'll do ask data expression e. Just print that, and then we'll need to do print decl statement data declaration s. I'm doing it wrong. It's going to have it's going to have an expression for e. Okay. Oh yeah. Yeah, I'll just pass it that. Okay. Void print decl statement. The statement pointer, we already know that it's a declaration statement, so we're going to want to print the type, the variable name, and what we're assigning it to. We're going to also need to print out more things, more and more and more. So print token type, print left-hand expression variable, print right. Equal sign. Yes. Yes. S data decl E data assignment. Oh my god. Is that not disgusting? S data declaration. It's a pointer. Yeah. Oh my god. Ladies and gentlemen, is this not absolutely horrendous? There's a better way to do it, but that's just what I'm most comfortable with. And even to me, it doesn't look pretty. Let's just steal this. Abstract syntax tree count, printf, an equal sign, printing the equal sign, print expression, print token type. I guess we could do. Then we're printing the. Ugh. Yeah, I guess we can do that. Yeah, whatever. We'll just have a switch statement for whatever the actual type is. We'll have S data declaration type token or token type. Yes. If it's we'll just have int for now. Int. So we print the token type, print the equal sign, we print the right-hand expression. Let's print the left-hand expression. And now we'll need to add, oh, well, we could just do, yeah, here. Just copy all that out and then print expression S data decl E. This is going to be an assignment expression, and we can add a clause for that. Print assignment. That's where we'll paste all this. Okay. Print primary, print binary, print primary, then we'll have print variable void, print variable. Print variable expressions. I need to add clauses for that. Oh god, what did I do? I pressed some hotkey that opened up a new window. And we'll have expression assignment, print assignment, expression variable, print variable. What am I doing? Print variable. Is everything right? Print assignment. Okay. And so now if we have a variable expression, we're just going to print out that name. And so we'll do S, and we'll have var storage plus E data variable var offset into that storage. And I didn't do it right. Variable. Okay. And then, yeah. Okay. So we're adding to abstract syntax tree string count every time we print out one of these from the overall function. It's easy to get lost in the code. I'm just going to set it to 0. For the next print out, we're going to printf the AST string. And let's just see what happens. Oh, okay. We need to add a new line. Okay, cool, look at that. So this is the abstract syntax tree printing out. We have int x equals 1, int y equals 2, int z equals 0, and z equals x plus y. This is exactly the code that we entered, but you know, we step through all the tokens, we construct statements and expressions for all of them, and then finally we print them all out, and this is the correct representation for the abstract syntax tree. Look at that, people. So that's pretty nice. Pretty nice. What are we doing now? I don't want to add blocks or scopes or anything like that yet. Remember, the end goal that we want to hit, we're doing this like x equals 1, y equals, let's just do y equals 2. Now we want to try to emit bytecode for our virtual machine. EM test right here. So this is, if you remember the virtual machine little demo video I made, I was explaining how it works. And the end goal for this little language project is to figure out how to make the full chain of tools to break down a higher level language into a lower level language, like a full compiler. Everything that I've wrote previously, like I wrote the abstract syntax tree, I guess that's like, I mean, I guess you can call any of these tools by themselves a compiler or a part of a compiler, but I've written like an abstract syntax tree, I've written a stack-based virtual machine instruction emission thing. I guess that's its own compiler. And then for this one, I just wrote assembly and an assembler for it. And the assembler just takes that text and breaks it down into a bunch of simple instructions to loop through. So the goal for this language is to make a full compiler where you tokenize it, you parse it into an abstract syntax tree, or you can just emit the commands immediately for it, but I want to make the abstract syntax tree to verify it on my own, like for extra debugging information. And the next step is to figure out how to emit text instructions like this for every command, and then we're just going to copy and paste it in. So, and there's a lot of ways you could do it, and there's different methods, like three address code, or SSA. I can't remember. Static single assignment form. It's like static single assignment form. There's 3 address code. Ultimately, intermediate representation. Like ultimately, all of those bytecode commands are going to get broken down into IR, intermediate representation for me. And 3 address code. This is where you're trying to figure out, like, you have those variables like x, y, z, and assigning them. I think we can do this. Yes, let's try and figure out 3 address code. I think static single assignment form is a different version, or like a more robust or faster. I think it's an alternative to 3 address code. We'll just start with 3 address code. And I'm going to take another piss, but when I get back, we'll just start experimenting with that. But as far as we're concerned, the stream for today, like now we're just at the experimental part, the stuff that I don't quite understand. We have the basics of statements set up, so you can tune out here, because from now on it's just going to be experimenting for the next few minutes until I get too tired and my throat is too sore to keep going. But give me a little minute or two and I'll be right back. Okay. I'm gonna sit down. Oh well, let's keep going. Where's my stream? Is it still even up? I haven't looked at it in a while. Yeah, okay, cool. I'm still the only viewer. Sick. No one cares. No one's watching. This is awesome. I can just experiment. Fuck up the code for the next hour. No one's gonna care. So I guess I'll print out the abstract syntax tree separately, and then I'll make... This is gonna be silly. We're just gonna figure this out. We're gonna figure this out together. Let's look at AST string count equals 0 when we first set it. Huh. I do int. Oh god. Int AST string count. Okay. I have another one. Let's do 3 address code string tac 2048. Int tac string count equals 0. Okay, and this is where I'm gonna start getting. I've never done this before. I mean, I did some research last night, but I really have no idea where to begin. The address code, local count? Yeah, so we can say that X, Y, and Z are all locals, and we can assign them. How are we going to do this? Guess we could have locals. It's like just have up to 100 locals. And these will just store integers for now. Experimental, I don't know, tac, emission, variables can only be integers at the moment. Yeah, Yaladev, hi, how are you doing? I'm doing fantastic. How about you, bro? We are working on learning 3 address code for our compiler. Yeah, but I'm doing great. We're trying to figure out how to represent the code at a lower level than, you know, an abstract syntax tree or a higher level, or breaking it down into my assembly-like VM, which you can see right here. I'm going to try and figure out how to break down higher level code into assembly-like language, which I've never done before. So it's a new learning experience for all of us. So I guess print, we have that printing stuff. We can also do emit bytecode. Yeah. We'll just duplicate all these functions. We'll have 3 address code string count equals 0. Gonna loop through all those same statements, and we'll do like tac or emit bytes statement. And all this will do is, because we evaluate in our virtual machine, we're reading in strings, we're just going to emit strings for this. So that's what we'll do. We'll do tac string, 3 address code string. And of course we're gonna get an error because we don't have emit bytes yet. Let's go to, can I like press F12 and that'll, yeah, cool. Okay. Void emit bytes. Byte statement? Statement S. Or is it emit? Yeah, emit bytes. Okay. So we can just mimic all this. I could just jam all this code together. That good idea, wouldn't it? But at the moment, I just care about, let's emit bytes for declaration statement. Emit bytes, declaration statement, emit bytes for expression. Call this void. Emit bytes for expression statement. That is, oh, emit bytes expression. Okay. Let's take this. Change it to tag string, tag stir count. Okay. So we are emitting bytes for the declaration statement. And so I'm conceptualizing it. Every variable will have location on the stack, the VM stack. Based on local count. So we can do locals, local count plus plus equals whatever data dot this is tricky. Decal dot E, which is the assignment. Data dot assignment. Oh my god. This is brutal. Dot write, which is its own expression. Data variable. No, write will be. Do we need to evaluate it now? Yeah, this is where we're slowing down massively. But like, what if we have 1 plus 1? We're probably going to need to evaluate that. So we're going to need some way to evaluate expressions. Yeah, let's just let's comment this out. And we'll do void emit bytes expression. And so we're just going to handle primary expressions for right now. So we'll do switch E type expression primary break, got a case default emit bytes primary or expression primary. Bytes expression. Oops. What do I want to send in? We'll have an assignment. But we want to evaluate the right-hand side because the left-hand side of the assignment will be the variable that we want to put onto the stack. And we'll need to somehow map this variable to the stack. This is tricky. We could make a hash table for the pointer where we could like hash the pointer. Is that reasonable? How do we even access the... Can we like cast the pointer to an integer? What happens if we do that? It's like... I've never tried to hash a pointer before. get something bad. Printf. D. Set a breakpoint here. Do int s. One. Well, that's not very reassuring. What if we just print out the pointer directly? Yeah, so I wanted to get something like this. Like, it would probably be easy to hash something like that, you know? Yes, I think we need a hash map, a hash table. We need to map the variable name to a local position. Yes. So every time we get something like, we start working with hash maps, hash tables, and we need to make it more robust. I don't think we need to add buckets yet. I don't care about that. We only have like X, Y, and Z. And as far as I know, they won't collide with each other. And of course, once we handle more variables, we're going to start getting collisions in the hash table immediately. But for the moment, I won't worry about that. And so we're going to hash variable name check if it already has a local stored with it. Check if it already, if not, local is back to local. Okay. And then whatever that local is will need to be the primary expression, so int value equals, yeah, I guess we could do int get of expression. It's going to be a little hack right now, and we will assert that expression type equals expression primary. Yes. And then we will return e data primary t data integer. Okay. Difference in level. Wow. Lots of freaky stuff. Declaration statement, let's just see. Okay. Okay. Get value of expression, and we'll get statement, data, declaration, expression, data assignment, dot write. Okay, and this will return the value of 1. This is absurd. We're in uncharted territory so far. I don't think crafting interpreters definitely doesn't do it like this, and they don't use a register-based virtual machine anyway. And as far as I know, I haven't read any resources on how to make a compiler like this, so we're doing it blind. And it's going to take a very long time. And at some point, I'm just going to stop streaming because I want to take a break and then continue this on my own. And then tomorrow, once I have a better idea, I'll just like pump it all out like I showed you today. And then get to previously unexplored territory. I'm just rambling. So I guess we can have multiple kinds of hash maps. So I'm going to have hash table, hash entry, string, and the hash. I guess we can make another one. local hash table, locals hash table. We'll have locals hash entry. And for a locals hash entry, for determining value and position of a local X, Y, or Z on the VM stack. Probably call it something better later. We'll have the hash for it, we'll have the string, we'll have the value to push to the stack. And local pause. Position on the stack. Yeah. Yeah. I think that should be enough. How do I put this in? Split and move. Move right? Yeah, sure. Oh dear. We'll do length test date 4. Okay, cool. I just wanted to have it on the side. And then we'll still hash the string. We'll still use this, and we'll make void push to locals hash table. Still use that same string. Locals hash entry. Lentry. Why not? Well, I mean, no, it's just, we don't really need that. It's a different function. If we do hash equals hash string. Just copy all this stuff. I hate how when I copy it, it adds all these spaces. Probably just something I need to configure in VS Code. Okay. Entry string. So I'd like to make this function multi-purpose, where I guess I could. I can't remember how to do this. I've done this so many times, but every time it's different. I could first check. Yeah. Let's add another function. Get. Oh my god. I'd get locals hash table. And so with the string, try to hash it. Entry hash. And we'll just return a U32 for the hash. No, because that could also be 0. We could return a value that's larger than hash table size, and that'll be the error that we can check and say, hey, it's not in the hash table, you should add it. Now we can get a pointer. We'll get a pointer back, and the pointer can be null. So we'll do locals hash entry pointer, and then we'll just set it right here. Locals hash entry pointer entry equals null. Hash table. If the string is set, slot is already occupied. This is the success case. We will return hash table plus hash. Else return null. And so that will tell us if it's already in the table or not. And if it's not in the table, we'll push. Of course, we can come up with some better information later. But we'll have a string, we'll have the int value and the int local pause. Do all that. Value equals value. Local position. Yeah. Warning, return incompatible types. We call it locals hash table. Okay. push the locals hash table and get locals hash table. Wow. Got 1,500 lines of code already. Okay. I think that should be good enough. Then you go to emit bytes statement 12. Yes. Emit bytes declaration statement. I press F12 on it, but it's like no definition found. It needs to be right on the name of the function to press F12 on it in VS Code to actually go to it. So we'll get the value. Let's check if, we'll do get locals hash table. Oh god, I can't even remember what it is. Get locals hash table, I think that's it. And then we'll send it the string. Yeah. And the string will be var storage plus s data declaration dot e dot e data assignment left. I can just send this through get bytes for expression. Yeah, I guess I could do that. Void. No, I can't. No, I have no mental model for what I'm doing, so we'll just keep it like this. Assignment left dot data bar offset. That is nasty, and it's wrong. Too few arguments to call. Why? I just want to hand it the string. Get locals hash table. If the pointer is valid, let's do that here outside of the statement because we want to save that pointer. Locals hash entry equals this, and then if the entry is valid, I'll go in here. Get locals hash table, variable storage, statement, data, declaration. What is the declaration going to have? It's going to have type and the assignment expression. So I have data assignment dot left. Yes. Left. Dot data. Dot variable. Variable. Yeah, okay. Yeah, wow. Wow, that is so incredibly nasty. I'm sorry, people. We'll do... So if it is valid, else we haven't added it yet. And so then we'll do push to. And let me just get the, var string. Okay. Just replace that mess so we don't need to keep typing it with var string. We'll do value, and then the local position, so local count. Yeah. We're pushing it. And do we get anything back? Push to, it's void. I feel like we should at least get a hash entry for it, right? Like, get something back. Yeah, let's get another locals hash entry pointer back to it. And we'll return this. It's not. The slot is already occupied. Oh well. Let's just return null because we couldn't get it. Okay. Okay, I'm going to set entry to that. Entry is null. Push to table. We'll give the local count the value. Byte's declaration statement. Let's see if we even get here with our code. Okay, cool. So value is 1. That's nice. Let's print out the printf variable identifier. Emit Byte's decl statement. We just print out where we are so I know what the hell is happening. Printf identifier. Then we'll print out the string. That'll be var string. Step into it. Identifier x. It's not going to be in a hash table. Step in there, make sure that we can assign it. Yes. Yes, yes, yes. Okay, and the local position is 0. Good. Value is 1. Okay. We're getting there. And now what the what the hell do we do? So it's not in the hash table yet. This is the first instance of the variable. I guess we could just start, yeah, like we have nothing to lose, so let's just, let's start emitting commands for it. What the hell, you know? Man, this is crazy, dude. Yeah, I keep losing my position. Okay. Let's find tax string. Okay, good. Yeah. Let's take this. Okay. So let's just treat, like, even though I did 3 address code, like, let's just try and emit virtual machine bytecode for this directly. And so that will mean that we're going to mov. Let me look at how this code is set up. We're going to load. Well, this is loading into register. Set pointer, set frame pointer. Can I load to an address? So we're going to load like the number 1 to, yeah. Okay, bear with me. This is what we want to mimic. So we're going to, we have a new local. It has a value. We have the local position, which is, you know, its stack position. Just got a notification. We can do something like, this is the frame pointer. The frame pointer is going to start like at the stack position for any given function inside of our virtual machine. Like we call a function or jump to a label, and we're going to update the frame pointer to point there. And so based on that, we're going to need some kind of reliable offset. And we can start. Yes. We're going to need to allocate. We don't know the amount of locals yet. So we're going to need to allocate some amount of local space on the stack. We need to know ahead of time, right? Only after we know all the locals So we'll need to like retroactively understand the offset that we're going to use. Yes. Well, we'll figure that out. I'm thinking that we'll aggregate all of these commands and then dump them. And then at the top, once we've like hit the bottom of the file, we'll have like a count of locals, and then we'll offset the stack by that much and put that at the top of all the commands, and then we'll start doing stuff like load. And then in here we'll do, there in bytes of 4, it's a 32-bit virtual machine. So we'll do like local count. Yeah, because we're going to want to start at 1 anyway. So this will be 1 times 4. I guess we can do plus plus. Plus plus local count. Yes. So that'll be 1, the instant. Yes. Okay, so then this will break down value. And so in this case, this will break down into 4 or minus 4. We'll do like frame pointer minus 4 is 1. So that's what we're going to do. We're going to do minus, have some kind of number here. And then, yeah. And so we'll do local count times 4, and then the value. And it's running, so let's see how that looks. Or, no, we're going to want to load it. Just to allocate the locals. Then we're going to want to print the string at the end. Let's just like print it directly. Yeah. Let's just print it directly. Not storing them for now. This is just experimental. Oops. Value. Oops. Okay, now. Cool. Okay, look at that. Load. Okay. Okay, cool. So we're emitting the bytecode command from our higher level language to load a value of 1 onto the stack at this position, and then load a value of 2 onto the stack at this position, and then a value of 0. That's cool. Okay. We're getting somewhere. And of course I have another mental blockage because I don't know what I'm doing. Okay. Local count. Okay. This is going to be a hack. Bear with me. I'm going to start appending to that string. And we're going to need to parse everything. So we're going to need to handle this one last line. So yeah. We'll just we'll leave it as is, and then we need to handle the z equals x plus y. So we're going to need to take the z position in the stack. Yeah. We're going to need to do x plus y, put it into a register, and then load that register's value into the stack's position for z. And this will be an assignment. void emit emit bytes expression assignment. Expression E. We're gonna handle that. Emit bytes expression. That's up here. It's gonna need to do variable. We already have that. Primary. Oops. Let's do assignment and variable. Variable. Assignment. Emit bytes expression variable and emit bytes expression assignment. Assignment. Is that right? Yeah. Okay. So I think we're gonna need to do more of the stuff that we did here. We'll figure it out as we go. So we've already declared the variable into that hash table. Wow. Oh my god. Can I like disable that? Is there has to be a setting in VS Code I can use because that is nasty. Get value expression. So this is a variable, which means that eData variable dot bar offset. Yeah. Value of expression. We're going to need to look it up into the hash table. Value of expression. So the value will be, we're going to get a pointer back. Oh god. The var string, if, we're just going to assert that it's valid for now. We're not going to add any error checking. We're going to assert that the entry pointer is valid. And then we'll get the value of it with entry value. Okay. So we emit bytes for expression variable. What is that? What do we want to do with this? We could add another, like locals, int locals. We could do int current register. This is going to be nasty. This is going to be absolutely disgusting. So we're going to, our max register, our max int current register. Okay. And we can also define max register. 30 and 31 are reserved. 31 is for the stack, so we could, like 21. 30 is reserved. Frame pointer. 1 is reserved for the stack pointer. So it'll have to be, it'll be from like 0 to 29. Okay. And we'll just need to loop them when that happens. Okay. Okay. And we'll just check if we're above the max register, and then we'll loop back around. For this is a broken version of broken way to handle register allocation, I think. So we're going to read a local variable, and we're going to want to push it onto a register because we're assuming that we're going to want to do something with it, right? That's the assumption. I mean, of course, this is all going to break later. If Byte's expression variable, you're going to get the value. If the entry is valid, well, we can just do if entry return. Yeah. No, we're definitely. Yeah. Yeah, we can do if. You're going to want to omit some kind of error. We can do runtime error. Runtime only insofar as when we eventually hook up the virtual machine to this, we're going to want to prevent it from running this code if there's an error like this. Yeah. Printf. Bytecode emission error. Has no valid hash table entry. Yeah. And then we'll do bar string. Okay. Otherwise, we'll just keep going. We don't need to push. We don't need to do any of this shit. The value, we're just going to move onto register, onto the current register, the value. Yes. Value. No. No, we want to load. I think we want to load the value from the stack. So we're going to load from memory. Load onto this register 3 minus D. And this will be the local count. This will be entry local count, local pause, and then current register. Yeah. And then we can just do if current register is greater than max register, current register equals 0. Okay. This is all going to break as soon as we hit something more complex. Again, this is just experimental. I need to keep clarifying that. This is not final production code. I just want to see if I can drive something, no matter how broken, with the current state of this programming language in my virtual machine. That would be amazing. So I guess we'll test it. We'll need to evaluate it. So when we have an expression, let's say that it's a primary or a binary. We'll need to handle those. So if it's a primary expression, we're just going to assume that it's a number. Assume it's a number. Assume the result is a number. What Byte's expression assignment? Okay. The end result of assignment expression will be get the stack position of the variable assigned to, compute the result of the right-hand expression, load on register 30, left expression stack pause, we'll do, yeah, then we'll need to emit. Man, there's a lot of shit we gotta do. I'm going for. We just keep going. So we need primaries and binaries. Emit bytes for primary and binary expression. So this we'll need to do eDataBinary.operator if it equals token plus. We'll only handle addition. And of course it's not right. Operator.type. Okay. Or we'll just assert. Because I don't want to wrap this. Okay. Okay. And so we're going to want to emit commands. If it's a primary or it's a binary. Void emit bytes expression eData binary left and right. Oops. And then that will recursively call the, again, we can only handle primary or variable expressions. If it's a variable, we're going to load whatever that variable is onto the register, and then we're going to load the other variable onto the register. That's it to do. Let's just assert here, in case we forgot to do something like that, which we probably did. Well, no, we're only working with variables, so we can just ignore primary for now. That's fine. These will emit instructions like load onto register, local X, load onto register local Y, and then we're going to need to add onto the first register, int first register pos equals current register. That will increase the register, and then we'll do second register pos. Add this to this. First register pos, second register pos. Emit bytes expression, that's because we need to define it up here. Void emit bytes expression. Okay. So we can handle binary. We can supposedly handle addition binary expressions. Yes. Emit bytes variable. So these will both be variables. We're going to load onto register. Yes. So we are currently emitting the declaration statement bytes. And then the final one is z equals x plus y. The emit bytes for binary will handle that side. So value, this will be an assignment. So we're going to need to emit bytes expression, the right-hand side, eData assignment, right. Okay. And then we're going to load, yes. This will offset the register. we're going to want to load the result in that register to whatever the local variable is. We can do this. We can do another one of those. You're going to want to find the left-hand expression is going to be a variable. And so we can just do this. Yeah. We're just going to assert that E data assignment left type equals expression expression variable. Very hacky, but I think it should work. Entry, we'll do entry, local pause. Let's just see what happens. Okay, got an error because we must be accessing. Yeah, whatever. I'll debug this in a second. I gotta piss again. Let's just stare at that for a while. It's like I rage quit. Okay. Okay, we're getting there. Oh. Oh, okay. What's the problem? I don't want to look at this anymore. I'm tired. Okay. Assignment expression. Bar string, unable to read memory. Variable, that's just because I copied and pasted that. Yeah, that's an easy mistake. Left variable offset. E dot data dot assignment dot left. There we go. Okay. Load, load. Do we ever do add anywhere we're loading? 1, 2, 3. And then we never do emit bytes expression. Okay. Step into this. We never added the binary expression. Expression, binary, binary. Let's try it again. Oops. Okay. And I don't want that add in there. Okay. We're getting there. We're loading onto Z the results of 1 plus 2. Add 1 to 0. We're loading register 0 back into that address. Okay. Okay. We're getting there. I think this is everything we need just to get this basic test working, and then I'm going to call it. And say that our very shitty broken compiler is, I don't know, it's not done. It'll never be done. But we can say that we made the first baby steps towards our shitty broken virtual machine compiler. I'm blanking. I don't want to print out all the stuff in between. I pushed Z. I want to disable all the stuff. Or instead, yes. Instead of printing all this out immediately, we're instead going to replace them all with the tag string count stuff. Like this. Oh, count 4. Okay. And I'll just replace all these. Why not? I'll just print them out. I'll print them out too. We'll print them all out as we go and then have a final printout. I think that's everything. And we'll do down here, init bytecode. Init bytes, print the, yeah, okay. Okay. Okay, these are our instructions. These are our compiled instructions, and we'll do one final printout. We'll offset. We will need to offset we will need to subtract the stack by the total amount of, I think we can do 31, subtract this value from the stack, and then we'll move that value into the frame pointer. That'll set the frame pointer. So like fp equals the stack pointer. I think that should work. Then we can debug this more. We'll subtract d from that, and that is local count times 4. Compiled bytecode. Okay. We're going to subtract 12. Okay. There should be 16 instead. Let's just see what happens. So the next step is to load this in. We're just going to drop it in. And I guess we could do, I think I can only handle it if we do that. The number sign is for an immediate value. Load, add, yes. Okay. And so now in bm test Fibonacci, we're going to make a new function. Imagine that. Going to test REPL reg value. Just copy something smaller. Test system call. Test compiler. We'll drop this in there. Here. And this is a comment, and we'll just add 0, 4, 8, 12, 16, 20. Those are like the offsets of the instructions. And now, I guess I'll just make sure, like, we're just going to test that register 31 is equal to 12. Or, I don't even know. Let's just step into it and find out what happens. Okay, so we built it successfully. Test. Just do all those. Then at the end of it, we'll test the compiler. Okay. All this work, and it's going to fail catastrophically because we made some assumption about a virtual machine that we forgot about. But we'll get there when we get there. Compiled it, run it. Finished successfully. I'm running it, and it's not working. Why, God, is it not working? I'll just delete all this. I don't know. A.exe does not work. A.exe does not exist. Okay. Launch. VM test. Okay. Now, evaluate REPL entries. Okay. So at the buffer is sub 31. Yes. We have this in the buffer currently. We're going to evaluate it. We're looking at the internals of the virtual machine I wrote in the middle of last year. Skipping the white space. Parse advance. Scan token. Make token. Scanner advance. I can't remember what any of these do. This alpha. Invalid addressing mode combination. Okay. Well, that is great. Let's try again. Let's figure out exactly where the hell that happens. Parse token. Matching token, token sub. Parse instruction. Sub. Advance. We found a register. That's the destination. Register. Number. Instruction value. Parse the source operand. It's the source. Instruction value. No, number. Okay. Look up opcode. Instruction final opcode is 255. That's because we had an error. And I think that's because I can clean it up later, but I think the problem is that we did jump to 12. I think we just want to put 12 in there. I was inconsistent, and so I think we need to ignore that. Parse map invalid addressing node combination. Well, that's not good. That's still the same problem. Do I have sub in other places? Okay. Yes. I think I can only, okay. I think the problem is that I can only subtract registers from each other. So I'll need to do mov into register 0, 12. And sub register 0. Yes. 0 backslash n or let's see if that works. Expected colon after label definition at start of line. Making token identifier. I think I need I don't even know what's going on anymore. This is necessary. We need to do this to figure out exactly how to structure the bytecode we're going to emit for a virtual machine from our higher level language. So this is just an additional cost of leaving the virtual machine and forgetting exactly how it works. Line 1, error at expected colon after label definition at start of line. Parsed identifier at start of line. That can't be good. Load? Is it load instead? I think I replaced... Yeah, okay. So it's not mov, it's load. Load. And I think it's anything that it doesn't recognize, it's going to think is a label. Let me, expected colon after label definition at start of line. Can I like add a little thing there so that I can, token colon, parser consume. I can do that later. I can add more robust error handling later. Yeah, I'll do all this later. Again, we just want to get this working as soon as possible. Ignore everything else. Expected right after bracket register symbol. Expected right bracket register symbol. Okay, so we never added this instruction. I don't think we ever did. Line 4. Is there a way to get around this? Or do we need to push? That's going to be brutal. Plus 12. We push 30 down and then we add to it. Load. Yeah. Yes. What happens when we push? VM memory plus the register stack pointer equals register 1. Push register. because it starts at the very end of the memory, we subtract it down a little bit. Yes. Okay. So we want to add instead of subtract. I think I'm only allowing for addition. Okay. Add encountered 12 plus 0 equals 12. Well, that's not right. Use compiler. Okay. What is in registers? Yes. Okay. Where's that print instruction? Print. I don't have any. I actually, turns out I actually need to add a lot more functionality to the VM to do any of this stuff I was imagining I could do already. I guess that'll be another stream. Got to clean up the virtual machine a lot. We're going to load 12 into 0. That's interesting. I think we're generating the wrong instructions. Yeah, we're loading. Adding register 0 to 2. That is not what we want, and I'll figure that out in a second. I just want to make sure that this is actually working as we intended. Load 0, load number 12 into 0. We're going to subtract that from the stack pointer to pre-allocate stuff. Okay. Registers. It's not working. Okay. Load offset address to register encountered. Load reg to reg. Well, I guess we're going to start adding breakpoints. Okay, so we don't have push, we don't have calls, we don't have returns, we don't have syscalls. We have a lot of different instructions in here. Jumping, jump to label, jump to constant, load data, address to address. We don't have that. Load offset, register. Oh my god. Let's just, here, I'll just set a breakpoint for every single one because we're definitely compiling the code now. So next I just want to see how the instructions get executed one by one, and of course I can't do that yet because now we can. Okay, so the first instruction is we load 12 into register 0. And so that's going to have a value of 12. Okay, good. Let's go to the next instruction. And we're subtracting 12 from the stack register, which is going to push it back a little bit, 240. Good. Now we're going to move into register, whatever, register 30, the value of register 2. And so now they're both going to share 240. That's adjusting the frame pointer. Load offset register address to register. Okay, so now we're loading an offset in memory. An offset register address in memory. Okay. Let's see what the memory is. Register 1 is, oh, okay. Yes, I think I did that wrong too. Yes, I'm never actually loading them into memory. Really long way to debug that, but yes. Okay. Instead of doing that, I want to load into this address a constant. So this will be like 1 and this will be 2. Will that work? 12, 16, 20, 24. And I think that'll give us an error. Load, parse load, invalid address and combination. Okay. So I think what we need to do instead, I think I just need to start adding more instructions because we never handled that. Load, can I even do something like that? Okay, so I never added a case to load into memory. Can I load a register into memory? Load, 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 load. What are all my different load commands? Upload. Load register reg, load immediate to register, load label to register, load register address to register. What we're looking for is load immediate or register to offset. Load offset register address to register. Load register to register address. Okay, I like that. Load constant. Load data address to address. I don't think we have any load constants, so we're just going to see. This doesn't get evaluated anywhere. But we have indirect plus a register. Okay, and now we need to add command for it. Upload, offset. Okay. Let's make a brand new case. Case. Break. This is how you add instructions to your virtual machine, people. I didn't know we would actually need to do this, but of course we need to do this. So I can't remember, this has been a long time since I've actually done something like this, so we'll just do load register to register address. Encountered here. Register 1 is going to be, oh god, I'm going to break that into bytecode. That's going to be, yeah. We're going to access a register with an offset, and then register 2 will load into it. So we'll do register 1 plus offset. If it's like anywhere outside of memory, I'm going to check that. Then we're going to do if register 2 is anywhere outside of memory. Remember, we need to sandbox this. And then I'm going to do register 2. The memory, no, we're not going to do that. We're going to do the memory there will equal VM registers reg2. And then we'll do this. Load is going to equal we'll have register 1 offset register 2. Okay, that worked. And do we need to set up logic to... That should be able to emit. Yeah, so we should be able to emit something like that. We load it into our 4-dimensional array. This is floppy. This is like 10 megabytes of memory right here. But I just wanted something fast and lazy to like look up instant addressing. We just have like these commands that we're handling, and then we just send back a specific instruction for it. And of course it gets very cumbersome after a while. And let's go to test compiler. And now what we want to do is we're just going to load in 0 and 0, and we'll do load register 0, 1, load register 0, 2, and then that'll load that stuff into memory. Yes. And this is all getting fucked up. Okay. This is nasty. A little number sign. These are all messed up. I'm just going to remove these for now. We're setting the frame pointer, loading 1 into 0, sending that to the stack, loading 2 into 0, sending that to the stack, adding those together. No. I think this is all backwards. Yeah, I didn't think that through very well when we, what is it? Language test. Language test. I messed this all up. Okay. So first off, we never actually pushed the values into the stack. That's one thing we got wrong. I guess what we're doing now is I'm writing what the instructions should be directly, and then we'll reverse engineer them. Or make sure that the compiler spits out these exact instructions. Pushing that value into the stack, pushing that other value into the stack. And then we're going to load into register 0 4, and then register 1 will have 8 after we've already assigned them. Load 1 into the stack, load 2 into the stack. From the stack, load those registers, add them together, and push that into the stack. And then I guess I can just, for a little test, I'll do load into register 0. I'll load the result, which will look like this. And now we can check if register 0 has a value of 3. Okay. Okay, well that's good. Pilot. Registers. Okay, well that's something. Let's go back to where we issue all these instructions. We're going to need to add a lot of work to this. Okay. We're loading the immediate value of 12. Yeah, we're subtracting them. We're setting them equal to each other. Loading immediate to register 0. Invalid opcode. What is that opcode, pray tell? 255 probably. We probably don't have an instruction for loading a register. Yeah. Yeah. We're not getting back the correct command for it. Switch. PC bytecode. These are the instructions in the virtual machine. Oh man. My arm is sore. Invalid opcode. Can we print it out at least? Current byte. Token. That's where I tokenize everything for the assembler. Oh man. Yeah, most of the stream is just going to be called VM debugging. I need to rename this. This isn't statements. This is mostly just debugging bytecode emission. Totally lost. We switch based off of some unknown opcode. Current byte VM bytecode. Yeah, PC. Bytecode pm.pc. And this will be errors. Unknown opcode 30. Let's go to opcode. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There must be a better way. Push register. This is gonna be stupid. Oh god. But we're gonna do this. Just to help me debug it. Just going to print out every single one of these as a string, so I can figure out which one the invalid opcode is without needing to look at the text. Oh god, I did something. is going to be quite nasty. Don't know how that happened. Illegal. Okay. Code string. Now we can see what, no, of course not. Why would we be able to do that? In this section of memory, you want to access, cast it to an opcode. Is that what you want? Yes. Unknown opcode, opcode greater than. Why would we, okay, well now I just need to step through and figure out why that's happening. Patch compiler. Okay. We just need to remember how we parse everything. Parse instruction, load. Subtract. Didn't tell us what it was. New line. Switch parser current type. Type is open new line. Wow. I need to print out every single line I parse. This is ridiculous. Line 3. Let's just restart. This is going to take a while figuring out what the hell I was even thinking when I was making all this. Token load. I need to put this in a separate tab. Split negative right. On. Sub. Load. Load. This is going to be, let's say load. Where's the scanner at right now? Yes. Okay, so the next instruction will probably be the unknown one. Load, parse load. Okay. Okay. So in instructions, the source will be a register. The offset will be byte offset. Register plus 30. Okay, I don't think I ever allowed for adding load. Oh god. So the destination you can definitely load with an offset. But the source that you're loading into, I don't think I allowed offsets for that. And I just have been assuming that I have been allowing for that. So I guess we'll step through it all again and figure out where exactly it goes wrong. Load, sub, load, load, sub, load, 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 parse advance, generic load. The destination, we'll need to parse that. Bracket. Parse advance, going to be a register. Okay. And it's a number. Instruction value, it's going to be 4. Okay. Good. Indirect offset, it's going to be 4. Operand, indirect register offset. Okay. Like the debugger. Yes, yes, yes. Instruction, destination, address register offset. So it's indirect, and it's register and offset. Okay. Good. Yes. And then the source. Wish I had like a type. Source will be a register. Okay. Okay. The destination, the source, the operation. What is the instruction operation? It's a 0. It's a generic load. Okay. Yes, 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 yes. Okay. So we're going to look up register offset, register, and none. Let's go to the lookup table. Load, register offset. This will return opload register to offset register address 10. Return operation 10. Final opcode 10. Okay. Okay. I really need more. I never thought of it when I was making this a year ago. Of course, the longer you program, the more ideas you have to make it easier. But I'm going to need to add like printouts for every single line I'm parsing as I go through this in the future. This is just insanity, stepping through it line by line. Emit instructions. Okay. Okay, the next one. Please. Let's go back to instructions. Parse instructions, load. Okay. Okay. So now, let's go back here. I just want to see if I'm hitting instruction 10. I just want to see if I'm doing that right. So that will be as we go through all those instructions. Set a breakpoint all the way at the top. Yes. Okay, this will be the first load instruction. Load immediate to register. Then we'll do subtract. Then this will be load register to register. Load immediate to register. And then we don't have that opcode. Even though at 17, at position 17, I don't think I'm stepping right. Load 001. I somehow stepped too far. I think I have an incorrect offset in how I'm stepping through the instructions. Wow. Yes, that's why. Because it's not instruction 30, which is greater than. It's not that. I'm accidentally reading the register number that I want to use in the previous opcode. So that means that load immediate to instruction is wrong or not stepping correctly. Op, load, immediate to register. Okay. Let's do it again. Load immediate to register. Current byte is 4. What the hell? PC. Oh god. Oh god. Okay. C++. We're loading an immediate value of 12 into register 0. That's 2 bytes. Okay, cool. So we're at instruction 4. We subtract, and that puts us ahead another 4 bytes. We load a register into another register. Good. We're loading another immediate value. Okay, so at 16, at bytecode instruction 16, we're going to hit instruction 10. But we don't have it. Okay. So I might have copied the wrong one. And the instruction that we wanted, and for some reason I can't see history anymore in VS Code, upload register address to offset register address. I don't want that. I want op load reg to what even is? And I lost it, of course. We want to load a register into an offset register address. Yes. We want this. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is what we want. But I never... What the hell did I add to... Oh god. Okay. Can we see initialize repository? Oh god. Is this an older version? Was I doing all this work in an older version? This is ridiculous. Oh man, that's horrible. Okay, well let's just find every offload here, because I did it somewhere. Let's just do plus offset. Upload register address to offset register address. Yes, I think this is what I did. And this is not what I wanted. I want upload register to offset register address. VM register is greater than max memory. I'm not accessing memory with this, so I don't think I need to have this checked. I'm just checking if that register is valid. Oh man, I don't know. I don't know where it is anymore. I think this is it. Yeah. Offset register, address to register. Okay. Okay, so I want this, but I also want the other way around. Took me long enough, right? Oh god. Load register to offset register address. Let me just make sure that's valid. Command yes. It's going to be something like this. Okay, so the first register will be that. Yes. Load register address to offset register address. Okay. Just making sure all these cases are correct. I'll have the register and the offset, and then the second register. Register 1. I need to switch this around. Register 1 plus offset will equal whatever we have in register 2. Register 1 plus offset is not out of memory, not out of bounds. Register 1 offset register 2. Okay. Okay. Okay, I think that let's run it again just to make sure. But in registers, dude, it worked. We got it. We just needed to add the right command, and I need to add so much more debugging information. So you see in register 1, which is where we stored 2, we did that, and then we added 2 back into register 1, which gives us 3, and so this assert passes. So we got it. We did it. So now we just need to make sure that we actually print out these instructions instead of the other way around, which we're going to do. And then we're just going to, we're going to call it right there because I am so tired. And there's still so much more to do. Like after this, I would want to add, I don't want to add function calls yet because that's like more juggling with the frame pointer. Whatever, let's, it works. So let's just make sure that we can generate this exact sequence of instructions from the code in laying test right here. And so this will be another thing where we've got to jump all over the place and emit bytes. So we're going to subtract that. Yeah, we do that. Let me, man. Where the hell was I? Okay. Let's add this to the bottom. This is what we want to see. As well as, yeah, let's just generate those two. After every single instruction, we'll add a little. Let's even add, oh yeah, that'll be so cool. If we add a little comment and then the new line character and then the instruction count. That will be awesome. Yeah, let's do that. Automatically generate our own bytecode. Dude, this is so cool. Int bytecode count equals 0, and we'll increment it by 4 every time. Okay. Let's emit. Let's just check out all the emit functions. Emit bytes variable. Emit bytes for the variable expression. So what does it even look like? What does it look like right now? This is what it looks like right now. It's compiled bytecode. Okay. So this is a hack. We know it's a hack. We're going to do it anyway. We're going to load into 0 the local count. Load. Now we're going to sub that. Yeah. This reserves. So automatically this will reserve at the start of whatever program we generate, this will reserve the locals that we have so far on the stack. And then that will move the frame pointer, and then we'll generate all the instructions. And then you need to load that first instruction into the register. Okay. We'll just generate. Of course, this is an intermediate step. I'll need to add a lot more. I need to add debugging. Let me just do to do. Just for every line, we're going to do that. I'm going to need to add direct constant loading to local indices on the stack, local variables. Okay. So this is a little stopgap measurement, like, because I can't load immediate values, I don't have that instruction, I don't want to add it right now. We're just going to load an immediate onto a register and then push that register's value onto the stack. And so that means that we need to go to emit bytes for variable. We're going to do it right here, load. I had it backwards. I think I had it backwards. Emit bytes for expression variable. I think that's correct, but we need to add it. We do plus instead. Because to reserve space on the stack, we subtract from it, and then to access where we stored that variable, we add, so we can go back to that original position. So that should work for loading the values. Of course, the current register, I need to get this right because we don't have it exactly right. Oh yeah, I need to do current register. Oh yeah, okay, that was just stupid. Let me, instead of adding that current register plus plus, I'll add it after these instructions. There we go. And we only increment it there. So that should fix our earlier problem of, you know, like load 1 and then load 3. Emit bytes expression variable. Adding emit bytes expression assignment. I think this is where, yes. And we're going to want to we're loading the register onto the stack. Okay. I think this was emit bytes expression assignment. Do we do this for a declaration? No, this was different. Okay, so for declaring, so when we're assigning, we're going to assume that value is in the correct register, so we're going to keep it like that. We just changed it to a plus symbol, and then when we're declaring, we need to add an additional instruction to put it on the register first. So we're going to make this a register with the dollar symbol. We're going to, let's just set it to register 0 for now. Yeah, we'll just set it to current register. Local count, current register. We don't need to change it or increment it because it's just going to, when we're declaring them, we're just going to use the first register for everything. Oh god. Let's do these. We'll do load. And then we'll load an immediate value onto register, current register. Yeah. We'll need to do entry value and current register. Okay, let's see if this is a bit more correct. Load 12 onto 0, subtract them, move it. And we're still loading those onto the thing. It's not doing something right. Okay. So we're printing it out correctly, but we're not, we're somehow not storing it. I don't know why. Printf. Tag string count is 12. Load 1. So first we load 1, new line, and then load that offset. So that is getting stored. Compile bytecode. Oh. Load 12 sub, move them. That's strange. Oh. Okay. Yes. Yes. Okay, I want to do all this. This was just an artifact. Okay, so this will just be the total. We're not emitting any, again, this is a misnomer. I'll just need to rename them. I'll just call these byte. Yeah, instead of TAC for 3 address code, I'll rename it byte stir count. And instead of tag string, we'll call it byte string, short for bytecode string. Okay. Okay, so almost. We're just forgetting to add a new line right there. Okay. And let me just make sure that this is the exact same that we expect. Load 12, subtract, move, load 1 into register 0. We're going to add it, or move it to that position. Load 2 into register 0, move it to that position. We're going to load 0 into register. Yes, because this is, we are declaring, yes, so this should still work. And then we're going to load them both and then add them. Okay, yeah, let's just copy this back into our virtual machine, and if it works, then we'll call it a success. I need to do yeah, I need to do that. We'll run it. And did it work? Did it not work? No, no. Move because I forgot to, we need to do load instead. Okay. Just make sure that's the only problem. Registers, yes, okay, thank God. Okay. So I just need to fix that. And we're not doing mov anymore, that's my fault. Instead we're doing load. So I need to find mov and instead change that to load. And now we're going to do bytecode count plus plus times 4. And we'll do that backslash n slash slash. Is that it? Yes. Okay. bytecode count. Because I want to add a little comment and then the place we're at in the instructions, just my own little debug stuff. %u bytecode count 4. This looks very nasty. Trust me. Let me just make sure that works. Okay, yeah, check that out. Let me copy this over. One last time. I guess I can add this to every single thing. Yeah. Bytecode count. This is kind of nasty because I'm printing this at the start. I can just add some little hack to it. That's just us setting up the frame pointer. I can just assume we'll just have like start bytecode count. Yeah, start bytecode count will be 0, 0, 4, 8, and then we'll just start at 12. Whatever. Okay, that still works. Again, this is just another little hack to do what I wanted to do, byte string. We'll print out, wow, that is nasty, bytecode count. Do that. Just append this to everything and then do bytecode count plus plus times 4. And we don't want it to start at 12, we want it to start at 0, 1, 2, 3. Add it here. Quite nasty. Add it here. Yeah, let's just hope it works. Okay. Of course, it looks very nasty. We don't have, I'll add pretty printing to it later. Let's just copy that over and see if it compiles. Over here. Errors. Why are we getting an error? Success. Error. Why are we getting an error? Oh, okay, I just left a space. But if we straighten it out, we have correct offsets for everything. This is instruction 0, 4, 8, 12, 16. Did I do that by mistake? Yeah. 20, 24, 28. Okay. Okay. Just run it again, make sure it passes. Yes. Okay. So, ladies and gentlemen, we have generated correct bytecode for a very simple program. But this is just a demonstration of, no one's watching, whatever. We've just demonstrated a compiler architecture where you have a higher level language, you break it into expressions, you generate an abstract syntax tree. I'm clicking all the wrong places. You generate an abstract syntax tree out of statements and expressions, and then you feed those into some kind of code that can then generate bytecode. If you read crafting interpreters, you'll do a stack. If you want to make your own register-based virtual machine, you would write your own register-based virtual machine backend. And in my case, I'm just generating strings, which will print out the bytecode that I want to see with the correct formatting and everything. So you can do it, and you can see that we demonstrated a very simple program where we add 1 and 2 together with local variables x, y, and z. So you too can do it. It just takes a little bit of hacking, and of course there's a lot more to add. Like we don't have flow control like if else. We don't have looping. We don't have function calls. There's a lot of stuff we're missing. Of course, this is very brittle. So yeah, there's a lot more to do and a lot more testing that we got to go through. But I am pretty stoked. I'm honestly pretty stoked that we got this far. Here we go. This is the final opcodes that we've generated. Compile bytecode. Let's just get rid of all this. Don't need that anymore. We did it. So when will I stream next? I have no idea. I need to figure out, I need to learn more about 3 address codes. I need to learn more about how to represent these steps intermediately. This was all incredibly hacky, but still we figured out how to get it to work, which was pretty incredible. But yeah, thanks for watching. I'll catch you later. I'm very pleased with how it came out. So yeah, thanks.